Hello, everybody. Welcome to FSI 304. I just want to make sure you guys are in the right place. My name is George Smith. I'm a solutions architect with AWS. This is Rob Hunt, who's the VP of Software Engineering for Nasdaq. And we're going to talk to you today about Nasdaq's journey from a Redshift data warehouse to a data lake. I'm going to go sit down now, and Rob is going to sit here and give you a lot of detail about the project and the initiative. Rob?
Thanks, George, and thanks to all of you for coming today to this presentation. I'm hopeful that you find some useful information, possibly some inspiration as you consider your own data lake solution. So today I'm going to start with a brief introduction of Nasdaq and our data warehouse and talk about some of the business challenges that we've faced with that solution. We'll talk about our journey to a more modern data lake solution. And of course, that journey itself had issues of its own. And so George will come back and talk to us about the AWS Data Lab, which played a central role in addressing some of those issues that we faced. And finally, I'll come back and wrap up with a review of some of the results that we've seen so far. So Nasdaq is probably best known for the equities exchange that we run in New York, but we do a lot more than that. Nasdaq is a technology and services provider to more than 120 different exchanges, regulators, and post-trade entities in more than 50 countries worldwide. We're the listing home to nearly 4,000 companies, and we operate 27 marketplaces across North America and Europe. Today we're here to talk about the Nasdaq Data Warehouse. The Nasdaq Data Warehouse stores the most recent year of data from thousands of different internal and external sources across our enterprise. On any given night, we typically ingest about 30 billion records, and during times of high market volatility, we've seen that as high as 55 billion records in one day. This data warehouse supports lots of different business critical functions at Nasdaq, such as billing, reporting, surveillance, data visualization and search tools. Our economic research team uses it extensively. The data warehouse itself is a 70-node DS2 8XL Amazon Redshift cluster. Each of those nodes has 16 terabytes of storage capacity, adding up to a total capacity for the cluster of 1.12 petabytes. And we typically operate that at about a 90% capacity. One thing that's important to understand about this data warehouse is that we have service level agreements for delivering reports to our customers. And those reports are generated during an overnight process. During this window between market close and market open the next day, we have to load those 30 to 50 billion records into the data warehouse, and then we have to run our billing and reporting processes and deliver those reports to our customers prior to the opening of the market the next day. So before we start talking about some of the issues that we've seen with this data warehouse, I thought we would just take a short step back in time and review how we got to where we are today. In 2013, Nasdaq embarked on a project called the RMS project, or the Revenue Management System. The objectives of this project were to replace a legacy billing solution that was an on-prem solution that was expensive, limited in capacity, it was difficult to maintain, and we wanted a new solution that was lower cost, at least as performant, able to scale to meet future needs, and of course, at Nasdaq, security is of a paramount concern. So during that project, we worked with AWS and we selected Amazon Redshift. It was a very collaborative relationship between Nasdaq and AWS to make sure that that Redshift solution delivered what we needed. This symbol, which you'll see on this slide and many other slides, is a vague representation of all of our exchanges, all of the data that we have on-prem. It represents thousands of different data sources, files, databases, and we needed a way to get all of that data into our new Redshift data warehouse. So we developed an application called NDW Ingest. This was an on-prem solution for gathering all of that data from our on-prem data sources and loading that data into Amazon S3. We just stored the raw files there, and then the NDW ingest application would do a bulk upload of that data into Amazon's Redshift. We also rewrote the billing system, the RMS system. That was an on-prem solution, and its job was to query this Redshift database and generate charge details that would then flow to downstream invoicing and reporting systems. And of course, we built it, and so they came. The ad hoc query users started querying this data warehouse. In 2015, we undertook the NDW 2.0 project, and the goal of this project was to store data that was older than a year old in a more cost-effective manner than Redshift itself. So we adapted the NDW ingest application to store Parquet files in S3. For those of you who aren't aware, Parquet is it's a columnar data file format with some metadata that makes it efficient for applications such as Spark or EMR or Spectrum or Athena or Presto to query the data in those files efficiently. We implemented a Presto cluster to make the data in those Parquet files queryable. And at the time, we had some visualization tools and search tools that were now attaching themselves to our data warehouse and to the Presto cluster to allow users to retrieve that data. The results that we saw, we accomplished our goal of storing data more than 1 year old in a more cost-effective manner, but we did learn some lessons during this project. Effectively, this was really our first foray into a data lake solution. The first thing was that our Parquet writing was done after the fact. So we loaded our Redshift database, and then we wrote our Parquet files. And so the Parquet file writing was sort of the second-class citizen in our ingest process. For a wide variety of reasons, our Presto cluster was not really as performant as we wanted it to be. But to be honest, it was hosting data more than a year old, which wasn't as mission critical as the Redshift solution. And finally, we lacked a schema migration strategy. And basically what that means is that over time, a given table, the schema can change over time. And so unifying those different schemas for that same data set over that time period was a manual and cumbersome process. In 2016, we had seen the value of scalability and agility that we had with AWS in storing our data, and so we decided that it was time to start moving actual application workloads into the cloud. We wanted to go beyond seeing AWS as just a data warehouse in the sky. So we took that RMS system and we wrote RMS 2.0, which was a cloud-enabled version of our billing system. We also had lots of legacy on-prem processes for generating reports, and we wanted to modernize that report generation platform. So that report generation platform would query Redshift and generate reports and store those report objects in S3. We needed a way for those reports to be delivered to our customers, so we developed a report delivery portal called Report HQ that allows our customers to come in and subscribe and retrieve those reports. So let's take a look at some of the business challenges that we've faced with the solution that I just described. This chart shows the number of Redshift nodes in our cluster over the course of time. As you can see, we started off with, I think it was 17 nodes, and over the course of the last 5 years, that has grown to 70 nodes, which is where it is today. During that time frame, there's a few important things to understand. First thing is that our data warehouse has become the central source of truth for data within Nasdaq. And so not only did we have our billing and reporting processes querying that data overnight, but we also saw an increased workload against this data warehouse from a variety of other use cases, such as data visualization tools, economic research, surveillance systems. So over this time, the workload against our data warehouse was continually increasing. Also during that time, the amount of data that we were putting into that data warehouse was increasing significantly. We went from supporting one of our North American markets to all 17 of our North American trading venues. We went from ingesting 4 billion records per day to 30 billion on average, with peaks up to 55. That represents going from ingesting less than half a terabyte per day to more than 4 terabytes per day. So in 2018, we started looking at this upward trend in our cluster size, and we became concerned by it. One thing that we realized was that we were paying for thousands of CPUs, many terabytes of RAM that we probably really didn't need. The reason that our cluster was increasing like this was because of our data storage requirements. So this was the time when we started thinking about separating our compute layer from our storage layer, which implied a data lake solution. Also during this time, where you see the red star, was a time when market volatility dramatically increased. We had come out of a relatively quiet period in the markets, and in early 2018, volatility increased significantly, and what that meant was that we had to ingest more data. With more volatility equals more data coming off of the markets. And so you can see that with the steepness of the curve in 2018. We were increasing the size of our cluster at an ever-increasing rate. And when we started doing projections looking forward, we saw a brick wall in our future. We didn't know when that brick wall was going to happen. It could have been in a year or 2 or 5 years. We weren't sure, but we knew that this ever-increasing cluster size was going to become a problem. So during that time, we managed growth in a variety of ways. Obviously, we added nodes to the cluster. We added table prioritization logic to make sure that the most important data was being ingested first in order to ensure that our SLAs were being met for the report deliveries. We optimized and automated WLM queues. Basically what that means is that we would give most of the cluster's resources in the early evening hours to the loading process, and then shift that allocation to the querying processes in the early morning hours, trying to squeeze as much processing out of this data warehouse during that 12-hour overnight time period. We underwent lots of different complex resize events with deep copies. We dropped old data. We had to correct table sorting. These were complex resize events that took the entire weekend. Our engineering team spent more time tuning tables, looking at distribution keys, sort keys in Redshift, spent more time working with users to optimize their queries. We spent a lot of time and effort trying to optimize the speed at which we were ingesting data into Redshift itself. All of this added up to our engineering team spending more time maintaining the system in an effort to try to make those SLAs than they did spending time on innovative solutions to try to address the root cause of the problem. Some of the issues that we saw from that growth of data were that loads were taking longer, our billing and reporting processes were completing later, stressing those SLAs, and quite honestly, we were breaching those SLAs on a more and more frequent basis. Because of the sensitivity around those SLAs, our development team and operations teams were on edge. Any little hiccup in the system would result in 3 a.m. phone calls, everybody getting on board trying to fix the issues as quickly as possible. And when we didn't succeed in fixing those issues and we breached those SLAs, we ended up with unhappy customers. Our reports were late and they weren't happy. And when customers are unhappy, our business stakeholders are also unhappy. I'm sure you can all relate to that. So given that this is a financial services event, I'm guessing there might be some customers in this room that are customers of these reports. And I can tell you that when our business counterparts chose to fund the project to fix this problem, their number one goal was to address the problem with Nasdaq meeting its SLAs for report delivery. So stand by, help is on its way. We also saw increasing costs. We had these weekend outages for these Resize events, and when we did our projections looking forward, it was not out of the realm of possibility that we would hit the hard limit of the number of nodes that Redshift supports, which is 128. So that's the brick wall that I was talking about. It was out there, we just weren't sure how far away it was. So our cluster had become too big, and we needed a better way. So let's take a look at our thinking around the data lake solution that was going to address these issues. So this is the high-level architecture that I reviewed with you earlier. And when we looked at this system, we settled on two primary objectives for our data lake project. First objective was to take a look at our ingest process and drastically improve the speed and scalability of that ingest process. And we wanted to do that by migrating it into a fully cloud-hosted solution that would take advantage of the scalability that the cloud provides. Our second objective was to dramatically increase the concurrency and parallelism that our query architecture could support. With Redshift, we were always dealing with contention between our loading process and our querying processes, contention between our billing processes and our reporting processes. There was always contention to worry about, and we wanted a way to eliminate that contention. So let's erase that part of the architecture and look at what our initial plan was to replace it. So initially, we knew that we wanted to move our ingest into AWS. And we wanted to turn Parquet file writing into the first-class citizen of our ingest process. This, we believed, would allow us to scale and dramatically increase the speed of our ingest. Second, we knew that we would have to do some proof of concept work around what sort of query architecture we would use to query the data in those Parquet files in S3. We thought maybe it would be Athena, maybe it would be Redshift Spectrum, maybe it would be something completely different. So when we did our initial project work, we started out with our ingest. And so we first adapted an existing application called Charon, and its job was to go grab all those files and databases, grab all of that on-prem data, and store it in S3 in its raw format. The real difference here between Charon and NDW ingest is that Charon lives in the cloud, and it's a clusterable workflow solution. So we could run it on 2 nodes or 5 nodes or 10 nodes or 50 nodes, and we would have sort of real-time flexibility in deciding how much we needed to scale that solution. Next, we developed an application that we lovingly named Wally. So you might be wondering why we named it Wally. Well, so when we considered the purpose of this application, it reminded us of the title character from the Disney movie Wall-E. Wall-E would roam around a post-apocalyptic Earth, gathering up trash and compressing it into nice, neat little cubes, and then stacking those cubes on top of each other and keeping track of where all of that stuff was. So our application was doing exactly the same thing with our data. It was gathering up the raw data, writing Parquet files, sorting those Parquet files, making sure that they were just the right size, stacking them on top of each other in S3, and keeping track of where all of that data was using the AWS Glue data catalog. So once we had our Parquet files, we could now do our proof of concept work around the query architecture. We initially tested with Athena. We liked Athena. It was serverless, it was simple. We had our data there in Parquet files. We had the metadata in our Glue data catalog. We pointed Athena to it, and off to the races we went. But we ran into several issues. First, we ran a lot of queries against it at the same time, and we ran into concurrency limits. Luckily, that was an easy problem to solve. There are default concurrency limits in your AWS account that can be adjusted by your AWS account team. So they had adjusted those limits, and that helped with the number of concurrent queries that we could run. The next issue that we ran into was that a lot of our queries were written to run against Redshift. And there are some query semantics differences between Redshift and Athena queries. And also, a lot of our queries made extensive use of temporary tables or common table expressions, which at the time Athena did not support. So we sat those queries to the side and moved on. Next, we noticed that when we ran our queries, a lot of them were not completing. And we noticed that these were the very complex queries with lots of different joins. The data at Nasdaq is very disparate, and in order to get a result set back that makes sense, you typically require lots of joins against lots of different tables. And those queries were not performing on Athena. We spent some time trying to optimize the Parquet files, but really only saw minimal improvements. One thing we noticed about Athena was that simple queries worked really well and really fast. So we liked that, but we didn't really have that many simple queries sitting around to run. So our conclusion was that Athena seemed very well suited for quick retrieval of already flattened or denormalized data, but was not well suited to handle our complex joins that were part of our ecosystem. So we decided to try another route. Next, we tested with Redshift Spectrum. So we started with a 2-node cluster, and we ran some queries. We saw some long-running queries, some that just wouldn't complete, and so we scaled it up to a 6-node cluster. And this is the moment in time when we really saw the value of separating our compute layer from our storage layer. This was the first time that we had done a Redshift resize where we didn't have to wait for data to rehydrate to the new nodes. This was a very quick process, and that flexibility has value but in separating the compute layer from the storage layer. So things were better, they ran faster. Some of the queries that were running slow were now running faster. Some of those that didn't complete were now completing, but we still had others that weren't completing. So our conclusion was that Spectrum was promising because our scaling tests showed some positive results, but it still wasn't quite meeting our needs. So the outcome of the project at this point in time was that our proof of concepts were running a little bit behind schedule. Our business stakeholders, and honestly some of our technology stakeholders, were getting nervous. They were asking questions like, will this really work? Are you guys on the right path? Do you guys know what you're doing? And so we engaged our AWS account team and told them that we needed help. And so they suggested that we travel to Seattle and go to the AWS Data Lab and tackle our blockers in our project using our data and our queries. And so here to talk about the AWS Data Lab and some of the experiences that we had there is George Smith. George?
Thank you, Rob. All right, so as Rob said, my name is George Smith. You guys met me earlier. I'm going to talk about the actual Data Lab engagement where the Nasdaq team came out to Seattle and we worked through a lot of the issues that Rob discussed. Data Lab is something that we started, I think, late last year. Earlier this year, we started to really formalize it. And so Nasdaq was actually one of the earlier customers with Data Lab. Data Lab has a tagline, come with an idea and leave it as a solution. They had an idea, they knew what they wanted to do, they knew exactly what they wanted to do, which is perfect for Data Lab because Data Lab is a very intensive engagement where you're going to bring your design, modern data lake architecture. AWS is going to bring experts, and those experts are going to work through the issues, work through the architecture, apply best practices, and provide guidance. And then in Data Lab, we're actually going to build and test these solutions. This is not just training. You roll your sleeves up and you start writing code in Data Lab. And this happens very, very quickly. And at the end of the lab, you're going to walk away with a well-architected design and a clearer path to production so you know how to get from where you are today to where you want to be. Okay? First thing we have to do with Data Lab is we schedule a visit. When it's on the schedule, we get a Data Lab architect. We spend several meetings, and these meetings take a couple of weeks, where we talk to the architect about exactly what we're trying to accomplish and what Nasdaq's goals for the entire Data Lab, and then we decide on the strategy and decide what is needed to be successful. That's code for homework. Nasdaq had some homework before they can come to Data Lab. They had to go and fully populate a suite of test environments. I believe you populated 3 different test environments. Came into Data Lab, Wally did its job, put all the files into S3. They had 3 environments. They brought along all the code that was either running too long or not finishing, and any other issues that they were seeing as they were trying to migrate this project, and they brought the actual team that was doing the work. So once everybody arrived at Data Lab, we came in nice and early on Monday morning. I think the day started at 8 a.m. and they finished whenever we were finished. Clearly articulate the deliverable for all of the new people in the room. Within 2 hours, we had tests running. We were looking at consoles. We were reading query plans and rewriting code. AWS experts were sitting right next to the Nasdaq engineers, helping with whatever was coming along. We did a series of test runs, redesigned based on what the result of that run was, wrote some code, did another test, more redesign, spent a lot of time at the whiteboard and discussing possibilities, rewrote some more code, did some more testing, and that's pretty much how the week went for the rest of the week. Any of the experts that we needed, we do this in Seattle for a reason. That's where we keep the experts. So any of the experts that we needed for these technologies, the Data Lab team and the Data Lab architect would go out and get them and bring them to us. And the Nasdaq team was able to work side by side with all those experts. Those days were long. I mean, I think somebody in the Nasdaq team called this work camp or boot camp. I don't remember which one it was, but they were long days. We started at 8 and we finished when we made some progress. By the middle of the 3rd day, figured it out. We knew what the solution was. And I'm going to get into that in a little bit. And then spent the rest of the week trying to poke holes in that solution to make sure it really stood up to what we thought, or what Nasdaq thought a production environment was going to be like. Met the tagline. They finished the week with a well-architected prototype, understood how to get to production, but additionally made a lot of relationships with some of the AWS SMEs in the room. Those relationships exist until this day. We still get them on the phone, still have conversations with them, and increase the knowledge, or a much deeper knowledge of Redshift and how to manage an application running on Redshift and actually tune it and make sure it's healthy. Okay. So the first 3 bullets are essentially what solved the problem or what removed the blockers. Code had a lot of common table expressions in it. That defaulted to this style of even. That doesn't mean this style of even is bad. It just might not be what you want for that particular query. Used create table instead, gave access to disk keys and sort keys and disk styles, but eventually decided to create temp table. And I'll get into a little bit why that's the case. There was a master class in Redshift query, reading Redshift query plans, knowing exactly what to look for and how to tune it. Same thing with the console. You can gain a lot from looking at the console to make sure the query is processing in a healthy fashion. And in this model, this style of all became way more valuable than it usually is in a Redshift cluster. And that's because of the separation of storage and compute. I'll go a little bit into that in a minute. So just to set a baseline, Redshift is constructed with a leader node and with several compute nodes. Those compute nodes come in 2 sizes, 2 slice or 16 slice. A couple of flavors, dense storage or dense compute, but it's generally 2 slice or 16 slice. This was before yesterday's announcements. We actually did this Data Lab back in the January, February timeframe, so all of yesterday's cool announcements weren't there for us. Your slice is your unit of compute, storage, and memory. It's what does the work in the Redshift cluster. And they all process in parallel. And what you want to do, your goal is to keep them processing in parallel. Additionally, columns, when you insert a row, each column is going to take a megabyte of memory. So if you have a 10-column table, 1 row insert is a 10 megabyte space allocation. This style of all will ensure co-located joins. There's two types of joins, co-located and broadcast. Broadcast means you're transmitting data across the network. Co-located means everything's happening inside one of these compute nodes. Obviously, co-located is faster. Okay? So with this style of even, you're going to be inserting a row in every single node in the cluster in a round-robin fashion. This is really great because it evenly distributes the data and thereby evenly distributes the work. The problem is, if you've got two disk style of even tables, you're always going to be doing broadcast joins. That becomes problematic and may cause performance problems. With disk style of all, you get one copy of the table on every single node, and it goes into the first slice of the cluster. What's good is you've got a copy of the table on every node, so there's no broadcast joins, but there's a limit. There's only so much you can fit on the node, so we pretty much say this works well for tables with less than 500,000 rows. Probably you can go up to 1 million depending on your data model and what kind of table you're inserting, how many columns, et cetera, and what kind of data is in that table. This is a sample query of what was working. We have this common table expression here on the left. On the right, we replaced that with a create temporary table. The value here is we get access to a distribution key. So now this table is being created with a distribution key that's going to work for the query. This is just a sample query because the actual queries that we were working with, or the Nasdaq came with, were over 1,600 lines. They had 18 selects looking at 27 tables, processing over 7 billion rows in an individual query, and it was taking roughly 400 to 450 megabytes of, gigabytes of disk. Now, the key here is when we're separating storage and compute, that Redshift, the compute layer, is only processing the working set of data. When you have a data warehouse, it's got to store the whole 1 point whatever petabytes of data and manage that. When we're running in this model with this separation, the data lake model, it only cares about the 400 gigabytes that you're currently processing. That's what makes this style of all more valuable because you can use it a lot more often. Your data sets are much smaller when you're just processing a query versus when you're storing a petabyte of data in a data warehouse. And you can also change it by query. So exact same table, you could run with this style of all, this style of even, or this style by key. And depending on what your query is doing, you can change your temp table structure and it'll process faster. So here we have full access to the disk style and the sort keys here. So if this particular query uses a disk style of even because it's going to join to a smaller table, it'll be a lot more efficient. And the next time you use this table, you might want to do a disk style of key. But it's really up to you. You're actually creating the temp tables when you're running the query so you can change your underlying physical data model on the fly. Redshift is a parallel processing database. The goal with Redshift, or any parallel processing database, is to keep all those nodes working. Right? Data skew is a problem. With many data models, Nasdaq is working with stock symbol data, where stock symbols, trades, and orders and executions of the symbol data. That's what this database is doing. Does anybody happen to know what the most active symbol is on the Nasdaq market? What was that? You know, it's $1,700 a share. It's kind of hard to be active at $1,700 a share. It's actually the QQQ, which is the Nasdaq 100 ETF. That's the one that's getting the most of the volume. That symbol trades twice as many shares as the second busiest symbol, and like 10 or 50 times the shares of the lower volume symbols. So there's a lot of data skew in this type of data set. So you have to be able to manage that. And what will happen in Redshift is if you have data skew, is you'll have a 70-node Redshift cluster. The query will start. All those 70 nodes will start doing something. And then one by one, those nodes will stop doing something. And when you get to the node that's running the QQQ, that's going to be running for a couple of more hours. That's not what you want. You want to get all those nodes working evenly. So With that type of data set, you're looking at a disk style of even, puts it all over the cluster, and disk style of all for whatever tables you're joining to. Keep all those nodes working evenly on the same size data set, and it processes it much more efficiently. And that's one of the things that the team is doing. They're basically looking at even and all and matching up the appropriate distribution keys so that they can get the Redshift cluster running as optimally as possible. So when you're looking at distribution keys, you're thinking about your joins. What am I going to join this table with? And this is going to define how you're going to distribute that table. And you want to avoid broadcast joins in most cases. Everything in this is going to be in most cases. Because if you have very small tables, it's not the end of the world if you have to broadcast join to a very small table. When you have the really big tables that you're broadcasting that it really starts to hurt. When you're looking at your sort keys, you want to think about the where clause, where date equals X. That means you should be sorting on date. Or where symbol equals Y, you should sort on symbol, that kind of thing. And with temp tables, they'll write one copy of a table, whereas a permanent table is going to write two for high availability purposes. So that's why the team switched to temporary tables in the middle, and literally, the create temp table took half the time. Okay? I'm going to change this on the fly and just say tables should always be compressed and analyzed. There's no reason to even think about it. Always compress it, always run statistics and analysis against those tables. It makes the Redshift run better. So with an unsorted table, if you're looking for a date of like June 12th or so, in the left side, you need to do 3 I/O to get the data. On the right side, sorted table, you do 1 I/O. Very simple. In the database world, less I/O, faster queries. Now, Rob mentioned earlier that before they separated storage and compute, that they really weren't constrained on memory or constrained on CPU. Now, as we separated storage compute, and now we're working with a different model with Redshift, and we're probably going to have smaller clusters and things like that, we want to start to manage memory much more efficiently. So if you only select the columns that you need, the memory space that table takes in Redshift's memory is only going to be 3 columns instead of 10 columns. If you have varchar 2048 columns, which I think in a couple of cases Nasdaq had a few of those, but you only had 200 bytes of data in it, resize those tables in your temporary table because all varchars will expand to take up their max size in memory. And you don't want to spill from memory with Redshift because that's equivalent to swapping. Swapping is bad. It slows everything down. And compression in all tables. Compression is going to give you fewer I/O to get the same number of data elements into memory. Now, data's sitting in S3, so we sat down with the S3 team to discuss some best practices and how to leverage S3 in the best way for use with Spectrum. So both the Spectrum and S3 team spent a lot of time with us in Data Lab. S3 is your physical data model now. You want to get it right. You can filter columns with your data format. Parquet is a column format. If you're going to pull in a row and you only need 3 columns, you're only going to touch 3 objects in S3. If you're going to do it with the CSV format, you're going to pull in the entire row and throw away 7 columns. So using Parquet is more efficient, at least in this particular use case. You can do Hive-style partitions. Right? So we can partition by date, and Spectrum will be smart enough to only go out to those buckets that have that data in it. So you don't have to look at the entire table. Optimizing the file size, which is what Wally does. When you're processing data from S3 and Spectrum, there's open, close, and metadata processing for every object you touch. You certainly want to spend more of your time processing data than opening, closing, and metadata. So a couple of rule of thumbs we had, 256 and a gigabyte is an optimal file size. And because the smaller file size, you're going to spend more time on the metadata processing and less time on the actual data processing. And if you over-partition your data set, you're going to get small files. With a petabyte, you're probably not going to over-partition, but when you're first starting out, you just kind of keep an eye on this to make sure you don't end up with smaller files. So, as Rob mentioned, the cluster was 70 nodes because of the amount of storage that was needed. Compute wasn't an issue at all. So now, since all data is in S3, the application teams are going to get smaller clusters. It's not going to be 70 nodes any longer. S3 has a feature called S3 Select. I think we released it last year, maybe right before reInvent last year. it's able to filter data at the storage layer. Select rows from table where symbol equals Amazon is only going to return in the Amazon rows to the Spectrum layer, even though there could be other symbols in that data set. So it's a way to keep, I call this push down predicates. It's a way to push those predicates down to the storage layer so the compute layer or the Spectrum layer has less work to do. Spectrum is going to do the partition elimination. It's also going to do some aggregations, some pattern matching. We heard earlier in the week that they added Bloom filters and other things like that to Spectrum. So Spectrum's getting smarter and is able to do work at that layer versus at the Redshift layer. And anything that's left, Redshift does and returns to the client. Also looked at the 2019 roadmap because, as you heard yesterday, there were 10 new features added to Redshift and enhancements added to Redshift. The team wanted to make sure that what they were designing into the data lake architecture was going to get those performance enhancements for free, that they didn't have to do anything. So they wanted to make sure the design was correct so that as Amazon increased Redshift's abilities, that Nasdaq would suddenly start going faster and performing more efficiently. This is what the architecture looks now. We can see Spectrum extending the storage layer down to S3. No more 2 petabyte limit. There's a brick wall's gone. You can go into the exabytes with data in S3. Redshift, when it queries data, sends the request to Spectrum, which, by the way, I think they changed to Lakehouse earlier. Yesterday, it was announced Spectrum is now Lakehouse, but I'm going to keep saying Spectrum. So it sends it down to Spectrum, and then Spectrum is going to decide what queries to send down or what commands to send down to S3. Once S3 gets the request, it does a lot of data filtering there. So if we have a 10 billion row table sitting on S3, but we only need 10 million rows, S3 is only going to send back 10 million rows. We don't have to worry about any of the other 990, billion rows? We don't have to worry about any of those. Spectrum is going to do any aggregations or any other processing at that layer, send the data back up to Redshift for further processing, and then less data is going to equate to faster queries in Redshift, and Redshift is going to send that data back to the client. So the team did arrive on Monday with an idea, jumped right in, 2 hours writing code. Wednesday, a prototype, Friday, a solution, and the partnership was built with several of our Redshift, Spectrum, and S3 SMEs that exist to this day. The Nasdaq team is now leveled up their Redshift skill set and have a clear path to production for their new data lake architecture. So at this point, Rob's going to come back and tell you what really happened once they got back to Nasdaq.
Thanks. Thank you, George. All right, so let's take a look at some of the results that we've seen so far. When the team came back from Data Lab, they brought back several things with them. And now the most important thing is not in this slide, but the most important thing that they brought back with them was a sense of relief for me. So we went into that week with lots of uncertainty, doubt, just more questions than answers about how it was that we were going to solve the problems here. And they came back with a clear direction on how we were going to solve our problems and take this solution to production and meet the commitments that we had made to our business partners. The next thing that they brought back was lots of information about how to optimize these queries to run against Redshift Spectrum. So the team encapsulated that information into some hands-on workshop materials and training materials, and they traveled and delivered that training information to our billing team, our reporting team, our surveillance team, and that empowered those teams to take that knowledge and adapt their own queries to run against Redshift Spectrum. The next thing that they brought back from the Data Lab was a deeper understanding of how Redshift and Redshift Spectrum worked. And that deeper understanding informed our thinking around the new target state architecture with Spectrum. As you recall, before we had one giant cluster of dense storage nodes, DS28XLs, 70 of them. And after our new target state architecture is really a set of dedicated clusters for each of these functional areas. If you recall, one of our primary objectives in this project was to isolate and protect different functional areas from contention with each other. We didn't want the billing processes to slow down when a surveillance process launched. And so by separating each of those functional areas into a smaller dedicated cluster, we protect those functional areas from contention with each other. Also, we discovered in the data lab that dense compute nodes are way more efficient at handling Redshift Spectrum queries than the dense storage nodes. The more CPUs you have, the more horsepower you get from the Redshift Spectrum fleet layer. So we go from 70 DS2 8XLs to about 20 DC2 8XLs. The benefits of this target state architecture are that, first and foremost, we have better scalability and parallelism. We now have the ability to run queries that have zero contention against our loading process, that have zero contention with other queries in different functional areas. The second benefit is that we now have basically infinite capacity for storing additional data. We could have the most volatile market days that we've ever seen. We could double the number of exchanges that we're supporting with this data warehouse or this data lake solution and support that with basically zero manual effort in terms of the amount of data that we're storing. And that's very appealing, given all of the effort that we spent around resizes of the Redshift cluster. There are some cost benefits to this new target state architecture. When you move from 70 DS2 8XL nodes to 20 DC2 8XL nodes, that represents a 75% reduction in reserved instance costs for Redshift. Now, granted, with Redshift Spectrum, you have to pay for data scanning charges, and some of those savings will be offset by those data scanning charges. However, even if all of those savings were offset by data scanning charges, which we don't think that they will be, we would still end up with a better solution for the same price. So better cost performance with this solution. Additionally, we now have more levers to pull for cost optimization going forward. We can look at our data storage in S3 and consider ways to optimize the cost there through using like infrequent access or intelligent tiering in S3. And finally, we have better transparency into our costs. By having our billing cluster and our reporting cluster and our surveillance cluster separated, they can be in separate accounts, and we can have down to the penny information on where the real cost drivers are for our data lake solution. We also have a greater variety in methods by which we can access our data. Previously, if somebody wanted to access our data, we would tell them to write a Redshift query. Well, today, they still can write a Redshift query and run it through Spectrum, but if they want to do something more sophisticated, then they can write a Spark process or an EMR process to run against that data. And they can do that without us worrying about them creating contention with our reporting and billing processes. So George asked me when we were going through these benefits, what's the real lesson learned? What is it that we really want to say? And he and I talked about it, and really, I think the message here is that if you have an opportunity to design a solution that has this type of infinite capacity, you should take it. You should design for infinite. If we think back to 2013 when we chose to use Redshift, that was the right decision at the time, but if these data lake solutions had existed at the time, I think that we would have, if we would have asked ourselves, will this solution be big enough? We probably said yes. But if you're asking yourself the question, will this solution be big enough? Just remind yourself that big enough will not always be big enough. It will not always be good enough. So design for infinite if you can. We've made some good progress in this journey. All of our billing processes, and almost all of our reporting processes have now migrated to Redshift Spectrum. The remaining systems are expected to complete their migration by January. And at that time, we will have one final Redshift Resize event. But this time, it will be a Redshift Resize party, because it will be the first time that we will have ever decreased the size of a Redshift cluster. We're already seeing good results. When we were doing this project, we completed our ingest process first. And we had a business need to process that data out of those Parquet files, but we weren't quite ready with our Redshift Spectrum approach. So that use case was satisfied by that team writing a Spark process against the data. So we're already seeing that the flexibility in query access methods is paying off. Recently, we had an outage, and in that outage, we were required to reload the entire day's worth of data starting, I think it was at, 6 or 7 p.m., or actually it was even later than that. But we had to re-ingest all of those 30 or 40 billion records, however many it was that day. And with the old system, we would have just said, oh well, we're starting late, we're going to end late, we're going to upset our customers and deliver our reports late. Well, when we had this outage, we said, why don't we just multiply the number of nodes in our ingest cluster by 5 and restart the ingest, see what happens. And we re-ingested all of the data for that day in about 2 hours. So we avoided missing our SLAs, we avoided upsetting our customers, and we did it for the cost of less than $100. If we think back to the initial objectives of this project, one of them was to improve our load times. And so when we look at the time by which we load 90% of our data, that's about 5 hours faster today than it used to be. So we just took that 12-hour window that we had to do our processing and saved 5 hours on the load process. We also see additional opportunities to make this even faster. We know that we can scale wide. We saw that during that incident that I just described. We also now have better visibility into upstream data delay issues. That last 10% where that blue line is kind of taking a long time to get through, that's not because our ingest is slow, that's because the upstream data isn't available yet. Well, now we can go look at that 10% of data and see what can we do to improve that upstream data availability. The second objective was to massively improve the parallelism and performance of our query loads. This chart shows one of our billing processes and how long it takes to run against all of the different markets that it supports. The yellow lines are how long that process took to run against Redshift Spectrum before we implemented the Data Lab optimizations. Those runtimes were about 3 times as long as our runtimes against Redshift, which are represented by the red lines. After we took those Data Lab optimizations and implemented them, the query times were 32% faster than they were against Redshift. And actually, this information is actually a little bit old. After rerunning these and sort of optimizing the cluster that we were running them against, the number is now 65% faster. So we call that the Data Lab effect. So we combine those earlier load times with the fact that we're able to run these billing and reporting processes faster than we used to be able to, and we've taken this 12-hour window and we've cut it in half. We now have 6 hours to do our work and 6 hours to recover if we have an issue, greatly improving the chances that we're always going to meet our customers' SLAs. Our next steps, like I said earlier, we're going to look at some cost optimizations. We're going to leverage colder storage classes, infrequent access, or intelligent tiering. We think that those dedicated clusters could be more dynamically sized. So if we have a Redshift cluster that starts out small but expands when the query load is increasing but then shrinks back when it's not really being used. That will improve our cost, but also our performance, we believe. And of course, we're going to continue to work with the AWS Data Lab partners that helped us with this project. And I just want to say one last thing, that the team that worked on this project, some of them are here and some of them are not, but I'm super proud of them, and I want to thank them for all the work that they did on this project. So thank you for coming, and I really appreciate you listening. And of course, don't forget to complete your session survey in the mobile app.